Then we can start. Okay, thank you very much for your introduction. Thank you all for listening. So what I will give you a short presentation on strength reduction technique with finite element method, in particular for slopes. And as mentioned before, this is a collaboration with the NAFEMS Geotechnical group I'm a member of. Now what I'm going to do in this presentation is, after a short introduction, I will try to describe the strength reduction procedure, and in some of the slides you will see the abbreviation SRFEA, so that means strength reduction finite element analysis based on a displacement-based finite element method. We will talk on the definition of the factor of safety, and because one idea of this presentation is to show that this is a reliable procedure for getting factors of safety, I will show some comparison with rigorous finite element limit analysis, and the term for this is then failure in some of the slides. Now there's an important issue we have to address, and that is non-associated plasticity, because that sometimes causes some troubles, and I will show also how you can overcome these problems. Of course, I show some examples, compare with limit analysis, compare with finite element limit analysis, and also with limit equilibrium. And just to show you the advantages of the finite element method, I will towards the end, show a back analysis of a failure. And then I finish off with limitations. That's important because you have to be aware of the limitations of this method, give some final advice, and come up with a summary. Now, what's my goal of this presentation? Now, first of all, explain what the strength reduction method is, and secondly, also explain what it is not. I think there is still some confusion in practice sometimes what is happening in the code during a strength reduction method. Then I hope to convince you that this is a reliable method to determine the factor of safety of slopes, and actually also for other geotechnical structures, but we are concentrating on slopes today. Highlight also some advantages compared to other methods such as limit equilibrium methods. And as I mentioned before, I want also to point out some limitations, because there are some restrictions when this method is applicable and when you have to be really careful in using it. Now, if we look at safety analysis in particular for slopes, I think most people in practice will still use limit equilibrium methods. That's fine. But of course, there are other methods available. As mentioned before, the displacement-based finite element method with a strength reduction technique, which will be the main topic today. But you could also use, of course, finite element limit analysis. That is a powerful tool, and I'm using it here to prove that the finite element based method is giving, under given circumstances, the same results. Now, just briefly on limit equilibrium, you're all familiar with that. You have to determine basically the form of the failure surface in advance. You have to assume some distribution of interslice forces, and the different methods do it in a different way. So Spencer, Morgenstern, and Price, Bishop, etc. You're all familiar with these methods. Now, sometimes the kinematic admissibility is not ensured, and then you need to perform a global search for identifying the failure mechanism with the lowest factor of safety. So you are defining basically the form of the failure mechanism, and the program then looks for you which one has the lowest factor of safety. By the way, at some stage we did some tests with different codes, and even with the simple method of slices, you do not always get the same answer using this officially the same method with different codes, and that is based. The reason is that you have different methods of identifying the critical failure mechanism. Now, the advantages, of course, are that it's easy to use, computational effort is very low, it's well established, and we have a long-term experience. Now, the disadvantages, it is not a rigorous method because, for example, you have to make some assumptions on the interslice forces, and that means it is not an analytical solution. Some people in practice realize that they think, well, this is an exact solution. It is not. Then I mentioned already, you have to define a failure mechanism a priori, and actually it may not always lead to conservative results, as I will show in one of the examples later on. Now, once we move on to the displacement-based finite element method and the strength reduction technique, what is happening if you do that? Now, let's assume you have a slope or any other geotechnical structure, and you do an analysis under, let's say, working load condition with characteristic strength and stiffness parameters. Then for the slope, for example, you would switch on self-weight, or in another case, you may analyze a cut in the slope, and at the end, you want to know the factor of safety. Now, as a starting point, you will have your characteristic strength envelope. And you see already here that I'm straight away talking about effective cohesion and friction, because as we will see towards the end, if you have more complex constitutive models, it's not so easy to apply this method. So in these working load conditions, you will have a more circle in various integration or stress points, which some of them may already touch the yield surface, but under working load conditions, we could expect there is quite a distance between the more circle in all the stress points and the failure envelope. Now, when you now switch to a strength reduction analysis, or a safety analysis if you want, then the code does nothing else than just reducing the effective cohesion and the effective friction angle step by step until equilibrium cannot be achieved in the numerical analysis anymore. So you do that, of course, not in one step, you do that in an incremental form. And what happens is that once you reduce in all the stress points your strength parameters, some of them you will touch the Moore circle in some stress points, then the redistribution, just in a way as if you would do a Norman analysis and you exceed the strength in some stress points, will start. That causes redistribution and you will still get a stable solution. But at some stage, too many of the stress points are at this limiting condition, and then the code cannot achieve equilibrium anymore. And then the simple definition is this friction angle, where you cannot get equilibrium anymore compared to the available strength you have, the characteristic strength if you want, that is your factor of safety. Now there's a note in here, you have an alternative way of doing it, that you run individual runs, new runs every time with reduced parameters. So you don't start from your working load condition and then reduce the strength, but you do a separate analysis with reduced strength from the beginning and see how far you can reduce your strength parameters. Now for simple slopes, the result is exactly the same. So we tried that with many students in master's thesis, so there's actually you get the same result. Now if you apply this method for more complex geotechnical structures, like let's say deep excavations with multi-level of struts or anchors, then you have to be a little bit careful. So that is what it is done, nothing else. Now, what are the advantages? Now, first of all, as I will show, it compares very well with rigorous limit analysis. So limit analysis, as we will show later on, will give you under certain conditions the exact solution. And you can produce that with a very small margin with the strength reduction method. Now, the big advantage is that you can use non-associated plasticity, and I would say as a standard case, we would never use associated plasticity except in certain special cases, and that can be easily introduced. There's no a priori assumption on the failure mechanism required. The failure mechanism will just turn out which gives you the minimum factor of safety. And the nice thing is, if you have a model for doing the displacement analysis to look at stresses and strains and displacements under working load conditions, you then can use the same model, so you don't have to switch then to a limit equilibrium program to get the factor of safety. So that is really an advantage and is an add-on, so to speak, because I think many people still think, well, finite elements is for working load conditions and not so much for failure, but you can do this as well. But I will come back later what you have to be aware of. Now, there's also the nice thing that, as with normal finite elements, of course, you can interact with the water. You can have very complex geometries, so that's not really the topic of today, but you can do that. You have the influence of the initial conditions taken into account. Now, again, for simple slopes, this influence is negligible. And you can also have an interaction with structural elements. And I will show an example later on, which is also important, but you have to be aware again that you have to think how you model then your structural elements. And finally, I think most of the commercially available finite element codes now have the strength reduction feature implemented, and I think also the finite difference code FLAC has it. So it's quite, it's readily available. Now, of course, there are some disadvantages as well. The computational effort is significantly higher as for limit equilibrium, but at some stage, if you have the model anyway for your working load conditions, so this disadvantage almost disappears. Non-associated flow may lead to numerical instabilities, so I will address that. That is an issue which comes up occasionally, not automatically, if you have, let's say, normal values of friction, dilation, etc. It's usually okay, but in some extreme cases, you can run into numerical instabilities. I would say it's not yet fully accepted in practical engineering because sometimes it seems that there's a misconception what this method does. And as I mentioned before, it's applicable only for very simple failure criteria like the Moore-Coulomb, where your failure is governed by effective cohesion and effective friction. And then there is something which is not important for simple slopes, but if you do a strength reduction technique for a more complex situation, now let's assume you have some stabilization measures in your slope and you have a load on top, etc. Then the strength reduction technique will give you only the failure with the lowest factor of safety. Now, the standards may require that you check other failure mechanisms and probably with different factors of safety. Now, that is what you cannot do, because this technique will simply give you the failure mechanism with the lowest factor of safety. And some years ago, I was in one of these working group of the Eurocode 7, and I can remember that we had a lot of discussions, because some people were of the opinion, well, I'm not interested in the ones who have a higher factor of safety anyway, but some were of course of the opinion that you have to check all these different failure mechanisms. So that is something you have to be fully aware of. And then also a word of caution. Usually these codes today do everything automatic. You say strength reduction or safety analysis or whatever it calls it, and then you have some default number of iterations or steps. Again, depends on the code. And if you just use it without checking, then you may end up with something like this. Okay, so that after 100 steps or whatever, you get a curve, FOS here, factor of safety here, and maybe displacement of steps, doesn't matter what you plot here, ends up like this. So this result is useless. You cannot check any factor of safety from this graph. It has to look something like this. So you have to get a stable solution. So if you add 100 more iterations or 100 more steps, it should not change your factor of safety. So that is really something which is very important, and sometimes it's not. So I see when I get some finite element analysis to check, then sometimes I see that this has not been properly done. What you also have to do is you have to make sure that you develop the failure mechanism which is reasonable. You can do that by many different means. You can plot contours of divitoric strains, or you can plot arrows of displacements, etc. It doesn't matter what you plot, but you have to make sure that you develop a clear failure mechanism. Sometimes, in particular in slope, it happens that you get a very shallow failure here with a couple of stress points, and the code will simply not converge to a failure mechanism you anticipate. So that is what you always have to check, because if you just look at the program and say, well, that's it, it may not be the answer you are looking for. Now, this is an important slide. It tells you what strength reduction is not. Some people still believe, so that is my experience, that they say, well, you do a strain softening analysis. You do not. Because if you would do a strain softening analysis, what you would do, you would follow a stress strain curve with a peak strength at the given strain, and then you will have a decay, you will have a softening to, probably it's better instead of residual, call it critical state, at another divitoric strain. So here you really follow a stress strain curve, but that is not so easy to do in finite elements, because you will get a severe mesh dependency if you do that. So that means you have to enhance your finite element formulation by what we call a regularization technique, such as a non-local formulation or others. So we do not have a physical degradation in friction and cohesion, because in a softening, in a strain softening analysis, you would probably have different rates for cohesion and friction. We do not have this in the strength reduction technique. So that is really a conceptual misunderstanding what the method is. So we are not following a stress path based on a stress strain behavior. We just follow a stress path which is basically determined by the stress point algorithms of the code. So that is something you have to be really aware of. We are not doing this. Now, in order to prove that it works, we did in Graz quite a lot of, actually together with Professor Sloan, some comparison with finite element limit analysis. Now, for those who are familiar with this technique, you know that you determine lower and upper bounds, and if the lower and upper bound are the same, you have the exact solution. Now that is usually not the case, but with this finite element limit analysis, the experience is that the difference between lower and upper bound is very small, it's a few percent, so you are very close to the true solution. Now with finite element limit analysis, you assume a rigid, perfectly plastic material, so you don't get any deformations, and an associated flow. And that is the key point, and I will come back later how we can deal with that. Just briefly, you determine a lower bound, and that means you satisfy the boundary condition, the yield criterion, and you fulfill equilibrium. So any load supported by this will be smaller than the true collapse load, and the upper bound satisfies the boundary condition, an associated flow, and you equate the internal work and the external work. So any load derived from the upper bound is an upper bound on the true failure load. So what you know if lower and an upper bound is that your failure load has to be in between these two bounds, but you don't know where it is. But as I said before, with finite element limit analysis, these days you get a very close, usually you get these bounds within a few percent. In the older days when you have to do it by hand, that was a bit different. Okay, now what are the advantages? So you have rigorous and upper and lower bound solutions. You have relatively low calculation time, and again, you also do not need to make an a priori assumption on the failure mechanisms required. The disadvantage is you can use that only with associated plasticity, so that's an inherent assumption of limit analysis. I would say it's not yet well established in practical engineering because there are not too many user-friendly codes commercially available. There are, however, some codes available, and you can use them for defining factors of safety in a very reliable way. So in order to show that you get the same result with these two methods, we looked at the homogeneous slope, we changed the inclination of the slope, and we looked at two materials. The first one is material Z1, that's basically a more frictional material with zero cohesion and a friction angle of about 35 degrees, and material Z2 with 20 cohesion and a phi dash of 25. So we are not dealing with a particular soil here, we just wanted to show the differences. Now, when you do this analysis then with failure, so with finite element limit analysis, most of the code use an adaptive mesh refinement, and that means you get a very nice picture of your failure mechanism. If you do it with finite element displacement based method, you have to be a little bit careful, and that is really an important graph here. So the actual geometry of the slope is not important at this stage, but I think it's the same one as this one. You see here the number of elements, and here the factor of safety. And if you are using this method the first time and you have no experience, then it is really advisable to run the analysis with different mesh discretization, because you see that it needs a certain number of elements to get a stable solution. Now, of course, this number depends on your type of element. If you use a very high order element, you can use less, but if you have not so, let's say you have only a quadratic element, then you need more elements. And the important thing here is that if you are too crude, if you're too coarse, then your factor of safety goes up. That means you are on the unsafe side. And that is something when you build up your model, you have to consider in the first place, because for those of you who are familiar with or doing a lot of finite elements, you know that if you just look at displacements at working load conditions, you can get away with relatively coarse meshes. And in particular in 3D, that is an important issue. Now, if you then at the end decide I want to do a factor of safety analysis, then you may be on the unsafe side because your mesh may be fine for displacements, but it may not be sufficiently fine for defining a factor of safety. So that is really, once you have some experience in that, it's not difficult and you will do the appropriate mesh. As I said, it's really an issue in 3D because in 2D it doesn't matter if you go a bit on the safe side and use a larger number of elements because run times, these times are not that crucial in 2D anymore. But once you have done that, you see that you have the failure upper bound, lower bound, and the strength reduction finite element. You get very much the same result. Now we have to come to the problem part. I mentioned already that we may observe instabilities for non-associated plasticity. And again here, just to highlight it, we took a very crude, a very severe example. So we have a friction angle of about 45 degrees. So, well, I'm in Austria, so we have these slopes which stand up with 40, 42 degrees. So they have, well, weathered rock, etc. So we do have these slopes, okay? But it doesn't matter, it was just making the point here. Now you see, if you take an associated flow, which you of course would never do, you get a factor of safety of 1.5. Now if you then take a latency angle of 15 degrees, you end up here with 10 degrees. So that's probably what you would do. You end up here. So that, first of all, shows that even for slopes where you would consider this as not a very confined problem, because many people think, well, the latency plays a role in confined problem. That's correct, it does. But here, even for slope, it makes some difference. Now, once we go to the extreme end of the latency angle, you see that we cannot obtain the solution I said before we should aim for. So you get a steady factor of safety, but it goes up and down. And the reason is because in that case, different failure mechanisms due to the non-associativeness of the problem compete with each other. And you see, this is the associated flow. You get a very nice, clear failure mechanism, but this is with the latency 0. The code is struggling in defining an exact or a very pronounced failure mechanism. So actually, you cannot do anything about it, except you take one of the methods I'm describing in a minute. Again, it's an extreme case, but you have to be aware of it happens also in other cases where you have large differences between friction and the latency that you run up into numerical problems. Of course, I have some colleagues from practice that say, well, I don't care, I just take an average here, that's fine enough. Okay, but that's actually your decision, and if something happens and you are close to the factor of safety, which is required by the standard, then actually you may be in trouble. So summarizing here, the latency has an influence on the factor of safety, even for slopes. And if you have a large difference between friction and latency, then you may end up in a sort of not very well defined factor of safety. Now, what can you do? Now, let's first come back what the codes usually do. I'm not 100% aware of how other codes do it, but in practice, what they do is when they invoke the phi C reduction, so the strength reduction, they keep the latency angle constant as long as the reduced friction is larger than psi. only when you reduce the friction that much that it would reach psi, the latency angle, then they reduce both. Now that doesn't happen very often, because if you would have to reduce your friction angle that much, you have a factor of safety which would be very high, and you're probably not interested in stability. So that is how the code, how Praxis does it, and I think most other codes will do it in the same way. Now, in order to check non-associated flow with displacement-based finite elements and finite element limit analysis, there is an option put forward by Davis some time ago. You see that you say, well, instead of using a non-associated flow, you use associated flow, but with modified cohesion and friction. So with this beta factor. So basically what you do is in simple terms, you transfer the non-associated problem into an associated one with different effective cohesion and friction. Now, as has been shown, amongst others, by Scott Sloan in his ranking lecture some time ago, this works very nice if you optimize for loads. But it does not work very nicely if we do a strength reduction, because you can do strength reduction with finite element limit analysis as well. It's a bit more difficult, but you can do it. So what we did then, or what we found out, is that you can use an alternative formulation for beta, and if you just don't get it in a second, basically what we do here is that we calculate this reduction factor beta at each step. So when we reduce friction, we also reduce the latency and work out the beta again and use that for the analysis. Now that gives very nice results, as we see on this slide. There are a lot of curves, but I will just point out the important ones. These are the two material sets I was describing before. So that is material set 2, the cohesive one. And you see here, all these lines, these are strength reduction, displacement-based, associated, non-associated, and the finite element limit analysis. Now the friction angle is low, it's 25 degrees. So the difference between associated and non-associated is not that large. However, if you apply the Fehler-Davis A's or the original Davis configuration, you are very conservative. Now, if you look now at the material set, which is more frictional, you see again that the associated finite element displacement based and failure gives you more or less the same result. However, if you do the original Davis approach, you're again very conservative. Okay, so it's of course nice to be conservative, but being too conservative is not nice either. Now, if you see, this is the strength reduction technique here with non-associated flow, and if you use then this modification of the Davis approach, we call it here Davis B, then again you get very similar results. So that is a way how you can overcome the problem of numerical instability also with the finite element displacement based formulation, if you want, because you can use this method in both analysis, but of course it's not implemented in the commercial codes. But what I want to prove here is that you are fine with a non-associated flow as long as you have not shown on the previous slide where you have a huge difference between friction and the latency. Okay. Now, of course, as I said, because here the friction angle is rather small, the effect is not very pronounced. And I think that's also the reason why many people thought you get the same result with finite element reduction techniques and limit equilibrium, because I looked in the literature, most people looked at friction angles of 25-30 degrees. And here the difference is indeed not very large, but once you move on towards higher friction angles beyond 35 degrees, then the effect becomes more pronounced. Here, just to emphasize the advantage, that's again a study we did with a student. So we have a slope, again the beta is variable here with different friction angle, effective friction angle, different alpha, so different slopes. Sorry, here is it, that's a mistake. So the alpha here is the beta here. And for all these analyses, we have 5 kilopascal of effective cohesion. Now, what you see is that for higher friction, you get a significant difference in the factor of safety, whether you take the latency 0 or the latency associated. And what you also see is that the limit equilibrium analysis, of course, in limit equilibrium analysis, the latency angle does never come in, but it gives the same result as finite elements with associated flow. Again, for low frictions, while the differences are not that much, and from a practical point of view, not important. But here you see, in that case, for example, you would probably be happy with the requirements of a standard with a certain factor of safety if you do it with associated flow, but with non-associated, you would not fulfill the criteria. Another issue, again, an extreme case. This is an analysis, limit equilibrium, where again a student was just running different friction, cohesion, etc. A couple of hundreds of analyses, and then in one he ended up with having a factor of safety of, let's say, 1.26, and then he did a praxis analysis, everything standard, he got only 1.09. Now what happened? In that case, you develop a tension crack here. Now in the finite element analysis, of course, this is automatically taken into account if you put the tensile strength to 0. So if you do, you can introduce a tensile crack, of course, in limit equilibrium as well. So if you do that here, you again get the same result. But of course, in limit equilibrium, this is an input, and you would have to decide how large this tension crack is. Whereas in finite element, you would get it automatically. And now if you allow for tension, you again get the same result as for limit equilibrium. So again, a message I will summarize at the end. You should, of course, set the tensile strength to 0 if you do a strength reduction method, except you have very good reasons for not doing so. Briefly, influence of structural elements. Again, it's not important to read all the numbers in here. So that is an example we took from the German working group. I'm also a member there on geotechnical numerical analysis of the German Society of Geotechnics. Excavation of a cut, shock grid, ceiling here, and 3 rows of nails. And the designer, for some reason, said, well, you can have a maximum of force in the nail of 75 kilonewton in the first 2.5 meters and maximum of 40 for the rest. Now, if you then do your analysis under working load condition, characteristic values, you end up being there, you get some stresses and displacements, and then you switch off, you switch on stability analysis, and you have defined the nails as elastic, you get a certain factor of safety. But of course, your failure envelope has to go beyond the nails, because the nails are elastic and cannot fail. But what you see here is that the forces in the nails are very large. Now, if you treat the nails as an elastoplastic material, then the situation is different, because now the failure surface can go through the nails, and then you get a completely different factor of safety. So the message here is structural elements in your system, you have to think what happens to these structural elements. May they let's say, form a plastic hinge. Let's say if you have a sheet pile wall or so, then you have to take care of that, because otherwise your factor of safety you're producing is simply not correct. So to finish off the examples, I will show a case history, and that's a failure here. You see it probably better here. It's geotextile reinforced slope on a steep slope, as shown here. So you see here the geotextile reinforced part. Well, we did it in 2D to get a quick check of what happened. It failed, as you could see here. It's not very clear, but you see here, of course, that you have a nice failure on that. Now the design was done based on limit equilibrium, and when a failure occurred, then we were asked to check whether we could do finite elements on that and see what the factor of safety was. Now, so again, this is the geotextile reinforced part. We gave this part a very high cohesion, so we knew that it didn't fail within this part, so we excluded that straight away. Ground conditions were sort of weathered rock, not always clearly identified, but in the geotechnical report for stability analysis, the parameters given were friction of 40 degrees and a cohesion of 0. Now, when we did a back analysis, and actually it didn't take long, so I think Franz did it, and it was just maybe 2 hours or 3 hours to do that. What we found out that the strength parameters based on the back analysis were 40 degrees. We left that and we needed 11 kilopascal in order to get the failure of, or you get a factor of safety of roughly 1. So that is reasonable actually, because of course the guy who did the geotechnical report wanted to be on the safe side, so he did not actually put in a cohesion. So what we hear from that, what we see from that if you would have done the analysis with 40 degrees and cohesion 0, you would have straight away predicted failure. Now, by the way, the FOS of the natural slope is about 1.25. Now that is so it failed at this height. So it even was not able to go to the maximum height specified, and of course the load on top could also not be applied. So we did then a back analysis using different methods, and also checked, of course, what we can do. And again, we compared it with finite element limit analysis, and just look at this row here. If you do a finite element limit analysis, a standard one with associated flow, you would have a factor of safety of 1.28. Now, if you do finite element displacement based with strength reduction, you will get about 1. So that is what we figured out first. So when we back calculate this one, we get about 1. Now, if you would assume a dilation of 10, so we would increase the factor of safety of 1.12. Now, when you do the Davis approach, as described earlier, you see that you also come pretty close. So this 0.98, 0.96 basically means failure. And if you introduce dilatancy, you get up 4 factors of safety higher than 1. Now, if you look at the failure and the SF and the strength reduction result, you see that the failure mechanism is very much the same. So I have to add that there was a concrete foundation here where the dam was based on it, and you had a kink in here in the failure surface due to the stress concentrations. Of course, you cannot capture that in a limit equilibrium analysis. That clearly shows that for this type of problems, finite elements or finite element limit analysis are still an advantage. Okay, and then then there was a reconstruction designed with a couple of anchors, etc. And now, of course, it is stable. So finishing off with the limitations and some advice. So the strength reduction method is applicable for simple failure criteria such as more Coulomb under drained conditions. I come back to undrained in a second. Well, actually in this line here. If we do an undrained analysis in terms of total stresses, then more Coulomb degenerates to Tresca, then it's fine again. But if you want to do an undrained analysis with a complex constitutive model in terms of effective stresses, you have to be very careful. Even with a more Coulomb, you have to be careful, because what do? You have a certain situation with a certain excess pore water pressure, let's say due to cutting a slope, and then you do a factor safety analysis. Now what happens is that you have two choices. Do I want to generate more excess pore water pressures during phi-C reduction, which is physically probably not reasonable, or do I freeze the pore water pressure? And you get different results. So what I'm saying here, if you want to do that, you can, of course, but you have to be aware that it is not that straightforward. Now, if you use advanced constitutive models where strength is governed by state variables, let's say the void ratio or the distance from the void ray from the critical state line, etc., then it becomes really tricky, and you need different techniques involving the modification of the finite element formulation, and an example is given here by Potts and Dravkovic. I've seen papers where people using hyperplasticity, where strength is basically governed by the void ratio, so they change the void ratio to arrive at failure. It can be done, it works, but one has to be careful when comparing these factor of safeties then with the standard one I'm discussing here. It's not the same thing. And also some people think they can get the displacements required for failure. That's of course not true. Once you have your factor of safety and you have failure, the displacements, they don't have any meaning, because it simply depends how many iterations or how many steps you have been performing. Some rules, I mentioned that already. You need a sufficiently fine mesh discretization. So if in doubt, check different meshes. A coarse mesh will be on the unsafe side. And actually the influence of the mesh discretization increases with the difference between friction and the latency. That's also coming in. You have to use very stringent convergent and error tolerances. Of course, I cannot give you any general rules, because each code uses that in a different way. You have to be clear that you have a stable factor of safety and no significant fluctuations occur. Tensile stresses should be set to 0. If not, then it will change your factor of safety, and you have reasons for it. Let's say if it's a cemented material or something, it's fine, but be aware that it changes your factor of safety. You should reduce the dilatancy in the same way as the friction angle, and you also have to make sure that you have a clear failure mechanism and not a very local one. And again, no displacements have no meaning. Summary. Strength reduction techniques are well suited to calculate factors of safety for slopes and for other geotechnical structures. Limit equilibrium analysis may be non-conservative in certain cases. Strength reduction compares well with rigorous limit analysis. You may have numerical instabilities with high friction and low dilatancy. You can overcome that with a so-called modified Davis approach, and that Davis approach can be used with finite element limit analysis and with displacement-based analysis. Okay, with that, I want to thank you. Here are a few references if you're interested in that, and I'm happy to answer any questions now in the discussion, or you can send me an email if you need further information. Thank you very much.
Thank you very much, Professor Schweiger. That was really interesting and really useful for, I think, practitioners or engineers far and wide as well. I think we've got a good amount of turnout from many different countries. So thank you for making this possible virtually from Austria as well. You said you'd be happy to take some questions now. I think we've got about 15 minutes, 10-15 minutes. If anyone wants to ask a question, please raise your hand if you'd like to say your question out loud, or type them in the chat and I'll read them out sort of one by one. We've got a first question in the chat from Joao Verde. Do you know of any commercially available software that includes advanced constitutive models where strength is governed by state variables?
I think the most commercial ones, they use plasticity and they use, let's say, single or double hardening, but I'm not sure whether these advanced ones are readily available. But of course, you can, well, they will be, well, I have to, if there is a platform which is called soilmodels.com, which is run by David Machine in Prague. And there you can find user subroutines which you can connect, let's say, to Abacus, Praxis, and other codes. And there, of course, are advanced models available. But I think the standard models in most of the codes will be hardening plasticity models, but not like hypoplasticity or Lade models or these very complex kinematic hardening models, etc.
I've got a second question from Jaya. What is the numerical modeling method used for Plaxis and how does it differ from SRFEA?
No, that's SRFEA in Plaxis. So that's strength reduction finite element analysis. But it's the comparison, it's different to FELA. FELA is limit analysis, but well, in the old days you do limit analysis on the back of an envelope, but now you do it numerically, and that is FELA. But Praxis or any other displacement-based finite element code will do the strength reduction technique in the way I described it. So FLAC is different, FLAC is finite difference, and as far as I know, they do it with running separate analysis with reduced input parameters, but they do it also automatically. But all the other finite element codes I'm aware of, they're doing it in a similar way.
Got a question from Nejan. Have you used strength reduction methods for unsaturated soil slope cases with transient poor pressure conditions?
No, that's a tricky one. No, I have never tried that. But of course you can do it. So, sorry, we actually played around a bit with it, but then you have to be careful what you do. So you can do your fully unsaturated flow condition and with rain infiltration, etc. So it can be done. And then you can switch on safety. But you have to be careful what happens then with the pore pressures during phi-C reduction. So one option would be to freeze it. That means during the safety analysis, you don't allow any changes in the pore pressures. So that can be done, and people do it.
Thank you. Another question, this time from Miguel. In which cases from the limit equilibrium analyses might it be more sort of or less conservative or not conservative?
I think so it's if you go to very high friction angle. So that is what I tried to show. If you have higher friction angle, let's say, I think up to 25, 30, you are more or less okay. But if you move to 35, and sometimes, you know, we have these soils with 40 degrees, then the chances that you are on the unsafe side are getting higher.
Got another one. How do analyses based on the strength reduction methods differ from outputs of, say, geoslope? So I'm aware, so something like slope W, where slope failure theories are used. I believe geoslope, slope W will be method of slices.
Yes, well, it's what I said. It's, I mean, it differs because you don't have to assume a failure mechanism in the first place. So that is a big advantage. And it's, I would say it's easy to use. You can use it also for quite complex situations, constructions, etc. So it's not that you have no assumptions on interslice forces and these sort of things. So which you have to do in limit equilibrium.
I've got a question of my own, seeing there's not too many more at the moment coming through in the chat. Do raise your hand if you'd like to ask your question directly as well. In your case study that you showed at the end, was it a purely 2D analysis that was done? Because I saw the profile view looked like a 3D problem was sort of going into the slope as well. I was wondering how much that might affect.
It would have been better to do 3D, but of course we didn't have time to do that because it was a bit of a tricky thing. It is in the area where they had the World Championships of skiing, and this was the path to the parking lot, and so they didn't want to spend a couple of months in investigating that. So we needed a quick answer, and then we thought that we would probably be on the safe side. Or reasonably safe, and we went then for factors of safety towards 1.3, etc. Because it's not always that 3D is giving the higher factors. So sometimes, you know, the 3D effects play the opposite role. So that is why we went for pure time reasons for 2D. But the nice thing was we didn't have to play around a lot. So, you know, about 3 analyses, we got the failure exactly where it happened.
Yeah, I've got a couple more questions. I think we'll have time for these 2 more that's come in through the chat. So the follow-up question is, if there's no defined failure surface in the strength reduction method, so in your displacement finite element, how does one interpret the failure pattern?
No, it comes. It's a misunderstanding. You get a failure mechanism, and if you don't get one, then your procedure fails. It happens sometimes that the situation is that complex that it cannot do. But when you get a proper factor of safety and a proper analysis, then you get a clear failure mechanism, as it was shown in one of the slides. The assumption is that you don't, let's say, if you do a Bishop limit equilibrium, you assume that your failure mechanism is a circle, for example, or you assume that it's a combined something. That is what you don't have to do. So that is the difference. So it comes out automatically, but if it is successful, it will give you a clear failure mechanism. But it's not restricted to circles or splines or logarithmic spiral or something like this, because it will just develop naturally going through the soil.
Another question. Could you explain a bit more, say a bit more about the limitations of undrained conditions, except when friction equals dilatancy at 0 degrees, so a pure sea cohesion.
Well, if you have a dilatancy in undrained behavior, you have to be careful because you get infinite strength. So I think in undrained analysis, you should put dilatancy to 0 anyway, at least with more Coulomb. Okay. With other models, it's a bit different. But you have to be careful because you have the constraint of 0 volumetric strain, or in numerical analysis, almost 0 volumetric strain, and that gives rise to negative excess pore water pressures if you have a dilatancy, and of course negative excess pore water pressure contribute to strength, so they increase your strength. So you have to be very careful. But if you do it in total stresses with Tresca, it's fine, because then you have an associated flow, and then friction is 0, so that means the latency is 0 as well. Okay, that's why I mentioned if you do it in total stresses, it's perfectly fine, because then your associated flow will give you 0 friction, 0 dilatancy, and the strength is simply governed by the undrained shear strength.
I think just one more time, enough time for one more question. How could strain softening progressive failure of, say, stiff clays be analysed if the strains from the strength reduction finite level?
No, you cannot do a progressive failure with strength reduction technique. That's what I pointed out in this one slide. If you really want to do a strain softening analysis leading to progressive failure, then you have to follow stress strain curves from your material, and there's no way this with a strength reduction technique. It can be done. So there are papers from colleagues of Imperial College and others, so it can be done, but you really have to be careful because, as I mentioned, once you have strain softening, your standard finite element formulation will give you a severe mesh dependency. So that won't work, and that's, for example, why codes like Praxis, they don't allow you to use softening at all. So that is a high-level analysis where you have to do something extra.
I think, yeah, thank you very much for the Q&A. I think it's been very useful, and particularly in the chat as well. Lots of people said thanks. So thank you once again, Professor Schweiger. I'm going to quickly present our gift to you for inviting the BGA ECG to the talk in collaboration with NAFEMS. It's a book from the UK showcasing projects from the past 200 years collated by the Institute of Civil Engineers. So I'll get this sent over to you.
Okay, thank you very much. Oh, that's really nice.
Yeah, a nice little engineering related pen with a spirit level and a screwdriver in there as well. But yeah,
okay,
thank you again very much for the talk. I believe we've got.
Thank you. My pleasure.
I believe we've got Andreas Silas also on the NAFEMS working group on the line. You'll.
Hello.
Good
evening.
Yep.
I'm just setting up. I'm wondering, can you see my slides?
Yeah. Yes, we can. I'll include this in the recording as well, just if that's okay, Andreas.
Yeah, keep it going. Right. So, good evening, everyone. I would like to. So I'm also a member of the Geotechnical Working Group of NAFEMS, and first of all, thank you very much to Helmut for presenting tonight, and also to you all on the call for asking so many good questions. I would like to close off the evening with a 10-minute presentation on Competency in Geotechnical Analysis initiative, so-called COGAN. Few introductions first. So you've seen the NAFEMS logo on Helmut's slides already. So NAFEMS stands for National Agency for Finite Element Methods and Standards, and was created in the 1970s by the UK government. It then became a not-for-profit organization, and is now funded by its members and guided by their needs. Its mission statement is to provide knowledge, international collaboration, and educational opportunities for the use and validation of specifically engineering simulation. So there's one big body that supports engineering simulation in the engineering community. Under this umbrella, there are several technical working groups, and one of which is the Geotechnical Working Group. We are 15 people strong. We recruit ourselves from academia, consulting, and software development. And our aim is to provide effective guidance on the use of numerical analysis in geotechnical engineering. We do this through publications. So you see there on the right, a publication that came out in the past few years on validation. We do seminars like tonight. And there's also the competency framework COGAN, which I will say more about. But to give a bit more background and introduction, I think most of people here will probably have experienced the numerical modeling project firsthand. And at the beginning, it is always perceived as a straight path activity. Budgets are agreed, deadlines are agreed, and a project manager allocates everything. But when it then starts going, and if it's reasonably complicated, it's nothing like a straight path. It can get very complicated. And it is probably well described in this sketch here. So on the left, initially, the expectation it's going to be a tick boxing exercise. And once we're in it, there are realizations, there are iterations, changes to be made, and there might be disappointment at the end of it, where budgets have been blown or deadlines have been missed, expectations by the client have been disappointed. So to keep on a straight line on that, the competency of the geotechnical analyst is really key. So when we talk about the competency, we try to encapsulate this. First of all, there are the core geotechnical engineer experiences that are well summarized in Berlin's geotechnical triangle on the left there. But there are other competencies that the numerical modeler for geotechnical problems really needs to capture, which are, they have to be competent in the use of whatever finite element, finite different code they're using. They have to understand the reliability and the appropriateness of the information that is at hand for the modeling. After all, rubbish in, rubbish out prevails. They have to have a good understanding on constitutive models that describe the soil behavior in the analysis that we are doing and how we calibrate them appropriately. And always we have to go back to past experience, which we can back analyze to pack our models to, so that when we then extrapolate to new new solutions, that we at least start off from a base where we know our models were able to predict reality. So coming now to COGAN. COGAN was originally funded by the European Union's Lifelong Learning Fund. And the initial step was to undertake a benchmark exercise where standard problems were given to numerical analysts to analyze, for example, a retaining wall, and then to provide their workings. And the results that were received showed actually large differences. And upon further investigation, it was concluded that probably there was a lack of skill amongst the analysts that led to those discrepancies. And out of that, Cogan then defined its aim, which is to provide a competency framework for numerical analysis. It tries to achieve this by, first of all, creating competencies that encapsulate what the numerical modeler needs to be able to do to provide safe solutions, but also to give learning modules, things to develop those competencies, and then also a web-based competency tracker. And I'm going to say a bit more about that. Okay, so Cogan used to have its own website. However, as of end of last year, everything has been moved onto the NAFEMS server. So if you now search for competency in geotechnical analysis on the web, then that should take you to the screen you see there on the left, which is the entrance portal to the competency tracker. There's also a video there that explains how to access the tracker. Also on the NAFEMS website, you will find e-learning modules and presentation recordings that give on certain aspects of numerical analysis. All this content is available for free. You just have to register on the NAFEMS website. The competency tracker, however, is currently a benefit to NAFEMS members. So if your company is already a NAFEMS member, you should have already access to this. If you haven't, NAFEMS would be happy to provide temporary access to everyone who is interested to have a look at the tracker and to understand whether that would be a useful tool for you to consider. Looking into the tracker now. So the tracker is actually not just for geotechnical engineering. As I said in the beginning, NAFEMS supports all kinds of engineering simulation. And so there are various disciplines that are in the tracker. But once you are in the Cogan core area, you'll find then that about 600 competency statements have been structured, first of all, in various groups. That starts from the basic geotechnical engineering capabilities on soil mechanics, consolidation, undrained drained analysis, and then goes into more numerical analysis specific competencies, and then onto practical application, for example, deep excavations, where everything is brought together for actual geotechnical problems. When you then sort of click deeper, then you find there are under each of these topics another window. In this case, it shows basically there are 30 competency statements made, and they are sort of different style. There are some for knowledge, some for more application and analysis. And there's also on the right there a difficulty level, level given here as shown as standard, that gives the person using the tracker an idea of what sort of level of difficulty is required here. And it's really intended to help the person to pace themselves in terms of developing. So you start with easy ones, then go for the more difficult ones. As this is so we then move on to select a specific competency statement. You get a new window, which then shows you the full competency statement. So the intention here is now, this is a task for you as a modeler to answer and be able to demonstrate that you understand how to answer this statement. If you are unsure and haven't got the right resources, you can then have, with many of the competency statements, have a suggested reference you can go to. Here in this case, it's even given down to the page where you can then read up to develop the understanding. And since this is a tracker, the idea is that the person developing the competency can then also record that they achieve the competency. So you can either do it in self-evaluation, or as here clicked as review by a line manager, or even having a review through an external reviewer on this if your organization wants to support this. You can then record how you have developed or how you have demonstrated the competency, or if it wasn't successful, you can map out in your comment how you will move on to do it next time. So it gives you a tool that, first of all, gives you access to the full repository of competencies that are seen necessary as for a numerical modeler, but then also allows you to do structured learning as well as recording your achievements. Right, some final words on work in progress. So we're currently working on expanding the knowledge base. So what Helmut has presented here today on slopes is something that we will reference now back into the tracker as resource material, so that people who sort of develop competencies on slope analysis can then go back and find these resources to train themselves. I've said there are more than 600 competency statements in the whole tracker, which is of course daunting on first sight, but it's a wealth of thought that has gone into that. And we're also looking in making this more accessible. So developing tools that can be used for planning of numerical analysis and checking of numerical analysis that go back and take account of these competencies. Right, final slide. So in conclusion, we think there's a real need to produce reliable and also reproducible numerical analysis in the industry. There is the Geotechnical Analysis competency framework that's available, also with a tracker to allow that development to be organized and to be furthered. We're looking at ways to make this more accessible and also to broaden the knowledge base to support that competency development. And on evenings like this, we reach out really to the community to first of all publicize this, because it's a resource that was created with taxpayers' monies and is there for people to use, but then also to see what other ideas are there or what other needs are there. So we are looking for collaboration on developing this further. So if you're interested and that want to give feedback on that or want to get involved, then you see our web email contact at the bottom there. So with this, I'd like to close. Thank you very much for listening. If there are any questions on Kogan or what we do, then feel free to ask now.
Thank you, Andreas. Is there any question? I don't see any questions at the moment. We've got a couple of just final BGA ECG early career group announcements. But there's a question in the chat whether the Kogan Udemy course is going to be made available again.
I must admit, I'm not aware of the Udemy course, but that must have been run quite a few years back. Is that fair to say? Does the person who just put the question in, does it remember that? Or Helmut, do you remember anything of that? I mean, Helmut was part of the group that developed Kogan in the first place.
I was originally part of it, but I'm not aware of this. Because once it moved to NAFEMS, I was not so much involved, and before that, because I stopped being involved when the European project was over. So I also don't know about this seminar. Sorry.
Yeah, so me neither. I'll have a look later. If there's anything I can find out, I'll post it back onto this channel.
I think that's it. Thank you once again. Just a couple of concluding slides for the BGA early career group. We've got a couple of events targeted at early career professionals. The first one being our annual mock chartered professional review talk. The event is now online because of various COVID restrictions, but please note the events link on our website and keep following on. And this will be particularly useful if you're sitting your professional review in the near future. There will be events where accomplished, recently chartered engineers will face sort of their chartered review again. So if you want to listen in and partake in the Q&A session afterwards as well. The BGA Early Career Group is also running a 6-week geotechnical series, a series of technical workshops on in collaboration with various companies involved in every stage of the geotechnical life cycle, from desk study to site investigation, I&M, lab testing. We're hoping to put in company visits to labs. So if you're based in the UK, in and around London, there may be some traveling required and you're interested. Our target is if you've got less than 2 years working experience. But if you feel you want to learn more about any of these topics, please see the link in the chat and register sort of an expression of interest. It's not yet a formal commitment, but we also like to hear your views so you can help us develop it. It will start in end of April is the current plan. Again, every time we'll do a call for the BGA Fund Award. It's to provide financial assistance to individual BGA members for further study and advancement of their career. Please do apply. Although there are specific deadlines on the website twice a year, applications are also reviewed on a rolling basis. Please get in touch with the BGA or us, the BGA Early Career Group, for more information. And finally, always a call for new members and members for the committee. If you're based in London or the Southwest or branching out, we're really looking for new members outside of London, north of the M25. So if you're there and you want to join in on early career group committee activities and planning future events and broadening your network within the geotechnical community, do reach out to us, either signing up to a newsletter on our website or emailing us directly, and you'll be very, very welcome to the BGA ECG committee meetings. And once again, to round things off, thank you very much to Professor Schweiger and Andreas as well for your brilliant talk. Very, very comprehensive. I thought sort of everything from background of all of these different methods, really breaking it down to sort of a simple introduction to a full case study at the end. So thank you very much. And yeah, NAFEMS look to be a really good opportunity for industry to really upgrade, I think, competency analyses, FE analyses overall. So thank you again. And this will be the end of tonight's event. Finish right on time at 7 o'clock UK time. And thanks for taking some extra time. I know it's late in Austria. Hope to see you all again.
Thank you for listening. Bye.